Hello, this is Group 29. Our project is to analyze and redesign a corded power drill. The electric drill utilizes a rotating drill bit to create different size holes. The purpose and application of the drill is highly dependent on the torque limits of the motor. For the market research, we found that the annual US demand for corded power drills was about 30 millions, with an annual growth rate of about 4.7%. We also estimated our annual production volume to be about 100,000 units per year. For our products, we identified two customer sets: professional users and home users. For our project, we are treating the rotor subassembly, which includes the motor and main drive shafts, as a single component. The main function for our product is to create a hole. The different tasks illustrate the how and why function, while assuring convenience while also maintaining protection.
This is our functional component mapping matrix, identifying how key functions relate to individual components. It is important to note that many components share the function of handling control. Through this matrix, we can also see that body A and B have identical functions. In addition to this, the selector and selector plate, as well as the cable clamper and guide, have some overlap that can be taken advantage of to reduce part count and complexity. As noted earlier in the presentation, the two customer groups have different requirements given their individual use cases that relate to durability, control of handling, and power. Through these considerations and the mapping matrix, we identified the platform and module components. This is the first of our module components, which will need to be different to satisfy the different customer needs. As shown, the rotor assembly on the left is smaller, resulting in a less powerful drill for the DIY customer, while a larger rotor on the right will provide a higher power level for the professional user. These different rotors will have a common interface at the pairing locations and will have accommodations for their unique rotor sizes in each of the body assemblies. This is the second of our module components. The professional user variant will have a larger, thicker body to meet the more demanding needs of the customer, while the home DIY user will have a thinner, lighter body to accommodate needs of that customer. Each of the two bodies will be designed to accommodate the unique rotor assemblies noted in the previous slide. This is our product family design assembly sequence. Through consideration, the drill head assembly was moved earlier in the process, allowing us to consolidate the module components later in the assembly.
We reviewed the assembly to determine which steps in the process required the most time and could be improved. Body B was found to have the highest assembly time due to the 8 screws required to attach it to body A and the rest of the assembly. The changes to improve body B also impact body A, so this part was also selected for improvements. Additionally, the cable clamper was found to have a high assembly time and was selected for redesign. Based on the quad chart, these components are ideal for redesign. Starting with the cable clamper, the original design took 27.9 seconds to install into the assembly. By redesigning the cable guide, the cable clamper could be removed entirely, which completely eliminated the assembly time associated to this part. As such, we reduced part counts, reduced fasteners, and increased part symmetry. These changes had no impact on the function of the part and reduced overall part cost and cycle time. On to body B, 8 screws are required to install this part to body A. This caused the assembly time to be 84.45 seconds. By moving to a snap fit design, we were able to reduce the number of screws required down to 3. This decreased the assembly time to 36.95 seconds. This had no major effect on part function and increased material cost, but reduced overall assembly time. The changes reduced the number of fasteners and increased utilization of snap fits.
For the DfA auto, we select two parts: the secondary axis subassembly, that is the axis, the main drill, and we also select the selector subassembly. Both those parts shows here on the function component matrix. One has low importance and low cost, a good candidate for part elimination, and another one has high manufacturing cost, that is a good candidate to optimize the assembly process. We apply the recommended guidelines on both. For the secondary axis subassembly, the cost went from $13.77 to $7.79, a 31% reduction. We reduce part count, we reduce the fasteners, the circlip in red, we combine the gear with the axis, and increase the part symmetry. For the selector subassembly plate, we also could reduce parts, we did snap fits and increase the part symmetry, and also add features to facilitate orientation. Also, the cost here went down pretty significantly, $13.85 to $9.61 for the 3% reduction. For the process selection, we look first on the body subassembly. This is a thermoplastic light part with 2 or 3 millimeter thickness, low tolerances, not so tight, and the two processes that were capable of machining injection molding, but due to the part complexity and geometry, we select injection molding for this body plastic part. The other part that we look on the process selection is the axis. Now that we combine with the gear, and the only capable process was machining with the precision machining to make the finishing. This is a very precise part with tight tolerances.
The design for manufacturing analysis, we are looking at the injection molded housing of the drill. The current estimated cost of the part is $3.80 for both halves, due to the complexity of the internal features. Using DfM Pro to evaluate, we identified the top 3 items to focus on for improvement to the manufacturing process. We have highlighted the design guidelines based on the DfM Pro results. We removed some side action in the tool by reducing the vent openings in the housing, lowered our DFA costs by replacing fasteners with step features. The cost chart shows the majority of the savings came from cost reduction to the tooling, resulting in 34% overall savings. Here we highlight the outer surface of the new housing with the proposed changes. Note the use of snap features in place of the mechanical fasteners. Based on the part and customer usage, we are maintaining standard injection molding tolerances and surface finish. The overall dimensions are not altered, so the component should achieve the same accuracy in assembly.
Now let's look in more details the secondary axis. The calculated total cost of the part is $14.1, which $3.15 represents the material cost, and the remaining is allocated to machining and non-productive time. Running the part in DfM Pro, several rules were pointed out, such as the sharp internal corners and non-uniform drafted features on the clutch area, as well as the minimal internal corner radius on the steps along the axis. After the suggested modifications, the part was redesigned considering the pre-shaping of the clutch area by die casting and adding a radius to all internal corners. There was no change on the product function or on assembly cost. Looking at the part estimation cost, using the analytical method, there was a significant reduction reaching almost 60%. However, the quotes from Hub website showed only 4.7 of improvement. The biggest difference is on the before calculus of the analytical method. The reason of the discrepancy come from the high complexity shapes of the clutch and gear that might need a different approach when calculated. Nevertheless, there was a cost reduction in both methods analyzed.
Our product will be offering additional strategies and services to improve customer experience and reduce the environmental impact. First, we will provide the customers with an opportunity to provide feedback on the product so that we can continue to optimize and refine the user requirements, resulting in improved future products that are better suited for the customer's needs. We would also like to provide training resources for use and maintenance of the drill to extend the life of the product and also utilization of the product for both customer sets. The product will also be designed with as many sustainable and recyclable products and materials as possible to reduce the environmental impact. And to take full advantage of this, we will also provide a service to collect and recycle the products at the end of life, to either recycle them or redistribute them to new customers at a discount. Finally, we will work to optimize the manufacturing process as much as possible through continued refinement and use of smart distribution techniques to optimize our shipping and reduce overall emissions. All of these services and strategies will be at little to no cost to the customer. In conclusion, we have worked to enable some dramatic improvements with both assembly time and manufacturing costs. Manual assembly times improved by 95.7 seconds between the cable clamper and body updates. Auto assembly updates resulted in a $10.22 part cost savings between the selector and secondary axis improvements. And finally, the DfM updates for machining and injection molding resulted in about $11 per part cost savings. Even with this, further improvements can be gained with additional optimization of the body component by reducing excess spacing and ribbing, in addition to performing DfM on the non-selected components like the selector plate and drill chuck. Finally, if we were to approach this product again, we would look at reducing from a 2-axis system to a single-axis system, reducing the part count and complexity significantly.
Thank you.